Hello world, what's up friends? I'm sure you're doing good. Gratitude to the giver of life, at the very least, for uh, the ability for us to be listening to me now and for the gift of audition, for you to be hearing me right now. So once more, you're welcome to Science Modernizers. And today, what brings us on board is to approach the same problem we tackled last time using a different method. So today we're going to be taking a different approach as promised. So it's our famous system, our famous man, our matchstick man here present. We are going to be approaching the problem with a different method and of course to arrive at the same answer. So we are going to be using the method of intersection of lines. Last time we used a method of sine rule whereby we had to use angles of depression or elevations to approach the problem. Today we are going to be looking at the lines. The initial lines we had here were this and this. So observe, we will attribute a coordinate system to our manual system. We will attribute the coordinate system or xy coordinate system here with the origin at point O, with the y-axis towards the first wall and the x-axis perpendicular to both walls. And observe, I have a line passing through point OB. I'll call this line 1, and I have a line passing through points AC. I'll call this line 2. So much such that point P is a point of intersection of line 1 and line 2. So follow as I walk you through the solution. So basically, the equation of a straight line is given in the standard form y equals to mx plus c, geometry, right? Or y equals to a certain, arbitrarily, y minus a certain y1 per se equals to m into a certain x minus x1 per se, right? Good. So that's the general equation of a straight line. So what we want to do is to get the equations of the line L1 and the line L2. From there, it permits us to get the point of intersection, calculate the two coordinates, and the man's height is going to correspond to one of the coordinates. So follow along. We will begin with line 1. Line 1, or the points 0, 0, and the points x0, 5 all belong to line 1, right? So by definition, we can use these 2 points to get the gradient of the first line. We will call the gradient of the first line m1. So m1 is going to be equal to change in the y all over change in x, right? Which is equals to 5 minus 0, you have 5 divided by x0 minus x, that's x0. And then we have the general equation of the line. We'll choose one point, we'll call it x1, y1, belonging to line 1. Let's choose 0. Let's take our x1, y1 to be equals to 0, 0. So that my line y minus y1 equals to m1 into x minus x1 is going to be such that I have y minus 0 should be equals to 5 on x0 into x minus 0. Oh, remember x0, right? From previous solution, x0 was this distance, x0, right? Back here. So what does this result to? L1 is such that we have y equals to 5 on x0 x. So that's line 1. We do the same thing on this side for line 2. So we will say that the points 0, 8 and x0, 0 belong to line 2, right? So with this, we can use this to get the gradient of line 2. m2 is going to be equal to change in y-axis. We have 0 minus 8, that's minus 8, divided by x0 minus 0 gives us x0. And line 2 is going to be defined by a certain y. L2 is such that we have y minus y2 equals to m2 into x minus x2, right? So we'll choose our point x2, y2 to be, let's choose any, I'll choose 8, I'll choose 0, 8, so that line 2 is going to be such that we have y minus y2, 8, should be equals to m2 calculated to be minus 8 on x naught into, you have x minus x2, my x2 is 0. Alright, so L2 is such that we have y is equals to minus 8 on x naught x, send the 8 the other way, it gives me positive 8 plus 8. So that's the equation of the second line. So what have we to do with this information? We have the first line, we have the second line. Point of intersection. At point of intersection, both lines have the same x coordinates and the same y coordinates. So we equate these two, right? So we do that here. At P, line 1 is exactly equals to line 2. So that we get 5 all over x naught x should be equals to minus 8 all over x naught x plus 8. So observe we have something x on x naught, x naught, x on x naught here. Can carry both of them to one side. By taking this to the other side becomes positive. I get 5 on x naught x plus 8 on the x naught x equals to 8. So that gives me 13, right? 13 of it. You have 5 plus 8, 13. 13 on the x naught x is equals to 8. We make x the subject because x here will represent the x coordinate of point P, right? So making x the subject, we multiply both sides by x naught on the 13. It gives us x naught on 13, into 13 on x naught x is equals to 8 x naught on 13, so that this falls off, right? And we continue this way. So observe this. If we have x naught equals to x equals to 8x naught all over 13, what does that imply? We can plug this into any of this equation because they're exactly the same at point P. Plug this into any of this equation to get the y coordinate. This corresponds to the x coordinate. So x in, I'll choose line 1, it's simpler. L1 implies we have y is going to be equals to 5 on x naught into x, which is 8x naught on 13. So the x naughts fall off and we are left with y equals to 5 times 8 on 13. That results to y equals to 40 all over 13. They were in meters, coordinate meters. So this lands us on exactly the same response, the same answer we had last time. I have it right here. So this was the conclusion of last time solving. Exactly the same solution, right? So by this, you see we've approached the problem from a different perspective and virtually the same solution and way shorter. As I promised, this one was more shorter. It's more of geometric. The other solution was more of trigonometric. So thank you for watching up to this point, and I hope you really did enjoy the fun of maths. God bless you, and please do not forget to like, leave some comments, and share the video with your friends who are equally science fanatics.